Okay, so here's a pulley question from mechanics. So two particles A and B are suspended over a smooth fixed pulley. Remember basically that the smooth part is important because we're making assumptions. A is 2.5 meters above the ground, and the particles are released from rest. Okay, again, remember that's important because from rest means the initial velocity is going to be 0. With the string taut and the hanging parts of the string vertical, okay, as shown by the diagram. So diagram's taken care of for us. After A has been descending for 1.25 seconds, so let's just make a note that A is going down, which conversely means that B must be going up because they're attached by that inextensible string. Okay, particle A reached the ground before B has reached the pulley. So as A goes down and hits the ground, B is going to be up here somewhere, but it's not going to hit the pulley. Right, so we have to show the acceleration of B as it descends is 3.2 meters per second. Right, okay, so let's go through our SUVAT. What information do we have? Okay, so we know that it's 2.5 meters above ground, so we know that basically A will go down by 2.5 meters, therefore B will go up by 2.5 meters. Okay, we know U is 0 because it starts at rest. Okay, we know the time because it takes 1.25 seconds to hit the ground. Okay, and we don't know what acceleration is. That's the thing we're trying to show. So now SUVAT calculations, if you think about it carefully, we know that S equals UT plus 1/2 AT squared. Okay, well, let's sub in our values. We know that S is 2.5. That's equal to 0, because remember U is 0, plus 1/2 of 1.25 squared times A. Okay, so now we just have to rearrange that, and we get that A is equal to 16/5, which is 3.2. That's shown part A. Okay, so what we've done is used our SUVAT calculations and the diagram showing us that this is 2.5 meters. Okay, right, let's move on to B. Find the tension in the string as A descends. Okay, well again, we know that it's a light inextensible string, so the tension for A will be equal to the tension in B. Okay, so we know the mass for B, so let's start with B. Okay, so I'm going to draw B. B is my particle. I've got tension there, and I've got the mass times gravity going down. Okay, and I basically pick my tension as being my positive direction. Remember, always pick the direction first. So I'm going to resolve in that direction. So my T is positive. My minus 3g is negative. That's equal to my mass, which is 3 times acceleration. Okay, so that means that T is equal to 3 times 9.8, which is 29.4, plus my 3a. I know what a is because I got a from part A. So that's 3.2. So 29.4 plus 9.6, that gives me 39 newtons. That's my tension. Okay, that should be fairly straightforward because all we've done is use the F equals ma and resolved forces. Okay, remember the only thing that's different here is the light inextensible string means that basically the tension is the same on both sides of the pulley because the string can't stretch, So those forces must balance each other out. Okay, so now we can move to C. Show that M, the mass of A, is 65/11. Okay, well, again, we can take this one individual part A, and then the tension is going up and the weight is going down. Okay, again, I'm going to resolve in that direction. So my T is positive and my mg is negative, and that's equal to my mass times acceleration. Now remember, we're resolving upwards, and we are this time working for particle A. Okay, now particle A is going down, so that means that the acceleration is negative. Okay, so now I've got T equals, I'm going to add mg to both sides. Mg is just 9.8 m. Okay, and then I'm going to take away 3.2 m. So that leaves me with 6.6 m. Okay, to find my m, so I need to substitute something for this T. Well, we just worked out the tension is 39 newtons, so I'm going to substitute that, because we said, remember, light inextensible string means tension on both sides is the same. So now I can make this 39 is equal to 6.6 m, and therefore m is 39 divided by 6.6, which actually gives me 65/11. So we have shown that that is the mass of A. Okay, just by using that light inextensible string meaning tension is the same on both sides of the pulley. Brilliant. Right, now we are on to D, and D is exactly what we've just been saying. Okay, that how we use information is inextensible. Well, that means that the tension on both sides of our string is equal. So now we can move on to E. Right, now E is where things get a little bit trickier. So there's some extra conditions in this. So two things are going to happen. So A, let's go back to our original diagram. So A is going down, and A is going to strike the ground, and B is going to go up, and B is going to have some momentum. So when A hits the ground, it's going to stop. But B is going to keep going up because it has momentum until it runs out of momentum, and then it's going to fall back down again. Okay, so it's going to move freely under gravity after A stops moving. So our question is, find the time between the instant that A hits the ground and the instant when the string becomes taut again. So we've got to work out how long B is moving for after A hits the ground. Right, so let's start from rest, because we need to work out how fast B is moving when A stops. So from rest. Okay, we know that from rest, that means that for B, remember this is all for B, U must be 0 because it's at rest. We worked out the acceleration. That was 3.2. And we know how far it's going to move, which is 2.5 meters, because if A goes down 2.5 meters to hit the ground, consequently B must go up because it's an inextensible string. Right, so let's use one of our CVAT calculations. So we use V squared equals U squared plus 2AS. Okay, well then V squared, remember I want the final velocity, so how fast it's going when A stops. That's going to be U, which is 0, plus 2AS, which is 2 times 3.2 times s, which is 2.5. Multiply those up, I get that v squared is 16, so therefore the velocity when a stops is 4. Right, now that's our part. Let's go part A. Okay, now we need to do part B. So basically what's happened here is that there's our pulley, okay, there's B, there's A. So A is going down and it hits the ground, and B is going up. We have just worked out that point where A hits the ground and B has moved up to this point here. So now we need B. So now A has stopped. Now the only thing making B move is its own momentum. So again, let's go back to our pseudo. We know that U, so the speed at this point is the speed that we just worked out. It's the speed it was going when A stopped. So that is going to be 4. Okay. Remember what happens? Okay, if we just talk about B now, B is going to move like that. Okay, and we are looking for the apex. Okay, we did this before with vertical motion. So V is going to be 0 because at that point it's slowed down, and then from that point it's only going to go downwards. So that's going to be the peak at the apex. Okay, we know that the acceleration is equal to minus 9.8 because the only force once A has stopped making it move is gravity, and that's in the opposite direction. And we don't know what T is. That's the thing we're trying to find. So now we link them together. Okay, we can use V equals U plus a T. Okay, so V equals 0. U is 4 plus minus 9.8 T. So 9.8 T equals 4. And therefore T equals 20 over 49. Okay, so remember the question was, right, that's all that time ago, find the time between the instant A hits the ground and when the string becomes taut again. So we've worked out the time from when A stops until the apex. So what happens? It goes up, and as Mr. Newton said, all things that go up must come down. So this is up, and as there's no other force acting on it, we have to assume it takes the same amount of time to come down, because the only force acting is gravity. So we double this. So T is actually equal to 40 over 49 seconds. And that takes care of E. Right. So the tricky part of that question is the last part. And it's just mechanics. It's just thinking about common sense, what's actually happened.